So I'm going to start off with a cheesy slide. So the kind of surprising thing about black holes is that originally they were predicted by general relativity. Einstein thought that they were unphysical because, as Baptiste mentioned earlier, the singularities, so a point of kind of infinite mass density and curvature. And normally when you have something that's infinite in a theory, that's seen as a big problem or a kind of a pathology of the theory. Maybe the theory is breaking down, something's going wrong. But then, that's what Einstein thought originally, that they were perhaps unphysical. But now not only do we have photographs of black holes, we can also hear black holes in a certain sense. So there's kind of no doubt anymore that black holes are kind of something that is part of the universe. And Stephen Hawking described them as the truth is stranger than fiction. So they're kind of like a unusual object. And the reason why they're so important, just for those a bit less familiar with some of the physics, is that black holes at these kind of points of infinite density are kind of very small in a certain sense. And that's normally where quantum mechanics, the first of Baptiste's owls, come in. And it's where the very small meets the very heavy gravity. So if we want to find a theory of quantum gravity, black holes are kind of a natural arena for finding a theory of quantum gravity. And so earlier, Baptiste talked about the two kind of owls, which were general relativity and quantum mechanics. You might think there's a third owl, or perhaps it's a bit controversial, maybe just a pigeon, of modern physics, which is thermodynamics, and that's going to be what I'm going to talk about today. So the kind of the story goes like this. In the 70s, Bardeen et al. Stated the kind of laws of black hole mechanics, and the details of this don't matter too much, but there's a property called surface gravity, and it's going to be constant when we have a stationary black hole. The first law says certain quantities are going to be conserved in various ways. If you change one, you're going to get an increase in another. And the second law says that the area of the event horizon, so that's the point of no return, the two-dimensional surface around the black hole, can't decrease. So those were the laws of black hole mechanics. And the surprising thing is, in a certain way, these mirror the laws of ordinary thermodynamics. So just to get a rough idea, in the first law, there's some small change in a quantity energy that's compensated for by these other quantities. You can see that the equation on the right-hand side looks kind of similar to this one. And so it looked like there was maybe some kind of analogy between the two sets of laws, which you might think is kind of surprising in a certain way. Thermodynamics is a theory about heat and work invented in the Industrial Revolution to understand the efficiency of steam engines. Kind of surprising that it might apply to black holes. Perhaps there's just a kind of analogy between the two, much like we find various analogies in physics. So one famous example, which is this thing on the right-hand side, is how we describe pendulum swinging. This equation in this box here tells you that it's obeying simple harmonic motion. So the kind of regular swing of a pendulum looks very much like how charge changes in a particular type of circuit. And you find simple harmonic motion all over the shop. It's kind of everywhere in physics, quantum fields, all sorts of places. And so you might think, well, the same sort of thing's going on here. We've got some equations of thermodynamics. They look quite similar to the equations of black hole mechanics. And thermodynamics applies to systems like gases, black hole. The laws of black holes obviously apply to black holes. And so there's a kind of similar situation going on to what we're used to in other analogies in physics. So, other cases there's kind of similarities between Newtonian gravitation and Maxwellian electromagnetism in various other ways. You might think there's a kind of similarity just in the mathematics. But then the story goes, Hawking radiation came along. And so the idea was then, well, at first it seemed like we had this suggestive analogy, but to really say that it was anything more than just an analogy would involve assigning a temperature to a black hole. That seemed difficult to do. Black holes gobble up everything in their surroundings. It seems like the only way to assign a temperature to them would be 0 in general relativity. But then, they're kind of like a perfect sync. But then Hawking radiation says that actually black holes aren't completely black. They're emitting thermal radiation. Think of kind of coals or embers in a fire kind of smoldering away. So black holes, in fact, emit radiation. Is very, very tiny amounts of radiation, but radiation nonetheless. And so then we can assign a temperature to the black hole. And this then led to kind of a much stronger relationship between black holes and thermodynamics, so much so that Bob Wald says the laws of black hole thermodynamics are the laws of thermodynamics. So in light of Hawking radiation, people then often want to say, well, really, it isn't just an analogy. There's an identity between the two things. Black hole entropy, so this S stands for entropy. Black hole entropy is thermodynamic entropy. And this, I think, is fair to say is the orthodoxy. Temperature is equal to the surface gravity. Area is equal to the entropy, or proportional to energy is equal to mass. So there's a kind of identity between these two different quantities. That's the kind of orthodoxy, I think it's fair to say, amongst physicists. But then some people have kind of been a bit more skeptical. In particular, in this nice paper by John Doherty and Craig Callender, they say, well, actually, I don't think it's anything more than an analogy. And that's partly because we don't really have kind of full-blooded thermodynamics. There's various differences. In particular, certain quantities change. For instance, surface gravity, the thing that's meant to be like temperature or identical to temperature, is not intensive. So an intensive quantity is something like pressure. If you have two boxes of gas and you put them together, the pressure of both boxes, if they're identical boxes, stays the same. Whereas if I put two boxes of gas together, they've now got twice as much mass, right? Or twice as many gas particles. So mass would be an extensive property, whereas temperature and pressure and things like that are intensive. So there's this difference between the two. So the question is whether there's just an analogy or whether there's something stronger, this kind of identity. And you might ask, well, why does it matter whether it's an analogy or an identity? And the reason for this is, on the one hand, if it's an identity, then it seems like there's a kind of unification of different parts of our physical theories. If it's really that thermodynamics applies to black holes and those quantities are identical, then cups of tea cool down, to have a kind of intuitive example, for the very same reason that black holes expand, because both increase entropy. And as we saw a bit earlier when Baptiste was talking about constraints, thermodynamics is used as a guide for finding a theory of quantum gravity. So finding a theory of quantum gravity is a very difficult thing to do. And the idea is that there's meant to be, so this maybe this is a bit tiny to see at the back, so I'll describe what it says. There's kind of two senses of analogy going on. So there's this connection between the thermodynamics of matter and the thermodynamics of black holes, or the horizons of black holes in particular is where lots of these properties might be thought to be located. There's this question of this as analogy or identity. And usually we have thermodynamics as the kind of macro level theory, talking about pressure, volume, temperature, and then we have the kind of underlying theory of statistical mechanics. So that's telling you about how fast the molecules in the gas are whizzing around. And so the idea is meant to be that in the same way there's this kind of macro-micro level relationship here, we can then use the kind of macro theory here to help guide us in the search for a theory of quantum gravity, because this is going to act as a constraint on how this theory can be, because it's going to have to give you the right macro properties. So that's why people really want to say that there's this analogy there's this identity between these two things that will then be used for these kind of epistemic purposes. So you might think, look, finding theories is hard. Take whatever inspiration you can. If it's just a formal analogy, you can take that kind of way of thinking about it. But lots of physicists take it to be something much, much stronger. So for instance, when Bekenstein was discussing something I'll introduce later, the generalized second law, he kind of, his reasoning went, well, if I don't have this law, then I'm going to get violations of ordinary thermodynamics. And if I don't have this connection, then things are going to go wrong in different places. So that really relies on something there being something much stronger than just a kind of mathematical similarity between the two. Okay. So the plan for this talk is I'm going to just focus on one part of this identity question, which is I want to understand what it means to say that the black hole entropy is identical to the thermodynamic entropy, which seems particularly difficult because there are differences between them. Normally, we don't think things that are different can be identical. And I'm first going to look at whether functionalism, so this is a kind of view that has become more and more popular in the philosophy of physics. How related it is to functionalism and the philosophy of mind, I think, is an open question, but the name has been taken, and whether that can be used to help understand these kind of identity claims. And I'm going to say that it can in kind of related case, but I'll also say, despite this, there's kind of limitations. In particular, functionalism can't on its own give us a ruling about whether this is a mere analogy. But I'll say that nonetheless, there's this clear evidence that it isn't just an analogy. And then the last part of the talk, I'm going to think about this more general question, which is how should we understand claims in physics where somebody says this quantity is this other quantity, or this x equals y. Okay. So I think probably everybody's familiar with functionalism, and the idea is that to be x is to play the x role. It's kind of more and more popular in philosophy of physics. If people want to understand how, for instance, three-dimensional space where the wave function lives can be recovered, can kind of functionally recover a three-dimensional space that we're used to. And I think the reason that it's helpful is that we can then emphasize that certain differences don't matter. And that's particularly useful if we're thinking about reduction, because if we want to reduce one theory to another theory, if we don't need them to be exactly the same, that makes the reduction kind of easier to have and kind of fits with how we, in fact, tend to go about thinking of inter-theory relations. And the reason why functionalism allows you to have this kind of benefit is that if the higher level concepts are just functional role concepts, then the realizer just has to play the same role, i.e. have the same behavior. So if there's certain formal differences between the two, that might not matter. Okay, and so one interesting question that I'd like to know your thoughts on is whether there's various different forms of functionalism, which ones people use in the philosophy of physics, I think is sometimes slightly underspecified, but I'm going to focus on this slightly more kind of Dennettian way of thinking about functionalism, where Dennett says that kind of functionalism is really just this kind of central assumption in science. Really, things, he says, matter matters only because of what matter can do. So the idea is that what we really care about is the behavior of different things rather than perhaps their kind of formal definitions in a certain sense. Okay. So in the case of, to give you the analogy of the philosophy of mind case, the idea is that if you can find something in this micro theory, the statistical mechanical theory, that plays the role of the higher level or macro theory thermodynamics, you can find the realizer, and that helps understand how both of these theories describe the same system. So in the kind of, so thermodynamics is a strange theory in many different ways, but it's often taken to be the kind of the typical example of a reduced theory, but there's lots of controversy about this. But when we look at different reductions, you see people saying things like the Gibbs entropy is the thermodynamic entropy. But there are certain differences between the two quantities. For instance, the Gibbs entropy makes reference to probability distributions, ensembles, whereas the thermodynamic entropy doesn't. So there's differences between the two. So Scar has this worry that these differences are going to block the reduction. So he says, how can the idea that temperature equals mean kinetic energy work, because you're identifying a non-statistical quantity with a statistical quantity? So how can they possibly be identical if that's what you think is required for a reduction? And so then the idea is that functionalism can be helpful because it allows these differences to be tolerated. So provided that it's not part of the functional role of temperature, that it's non-statistical. And provided that being a property of an individual system rather than an ensemble is not essential to the thermodynamic entropy, then it doesn't matter that these two things differ. So I think we should say that provided the Gibbs entropy plays the thermodynamic entropy role, and it has the same behavior, then that's enough. And likewise, provided that for an ideal gas, mean kinetic energy plays the temperature role, which, you know, I think the hard work is in spelling out exactly what those roles are. So in the case of temperature, it's that the quantity is identical for systems in equilibrium. I can say more about entropy, but I won't now. So the idea is that perhaps certain formal features like being extensive or intensive don't matter provided that black holes behave like thermodynamic objects. So put another way, you can think of the domain of thermodynamics as being extended from just thinking about systems like gases or other kind of ordinary matter systems. The domain of thermodynamics will be extended if the new objects behave in the right way. But the really difficult question is, what is the right way? So I think, you know, if to be a duck is just to behave like a duck, then someone says, well, what's so important about duck behavior? Is it quacking is the crucial thing? Likewise, you might say, what's the crucial thing that something has to do in order for it to count as being thermodynamic? And I think this is where all the hard work is. So this is an interpretive project about which things you think are really important to a physical theory, which I think is a lot of the work that's being done in philosophy of physics when people espouse functionalism. But this is quite different, right, from how other people sometimes think about functionalism in philosophy of physics. So it's very different from the functionalism of Butterfield and Gomes, for instance, where that's kind of a much more Lewisian way of saying, okay, I'm going to find the Carnap sentence of this theory and then look for that thing. So yeah, I'd be interested to know whether you think that these different forms of functionalism, whether they're kind of getting at the same thing in different ways or whether there's some kind of deep difference there. But the crucial question for this project of thinking about black holes and whether they're thermodynamic or not involves answering the question of which features of thermodynamics are essential. And so I think the crucial thing you need are equilibrium states, and you need the availability of a certain type of process, so quasi-static processes. And this is not, you know, other people might want to argue for other things as being really essential. I think this is the right way to think about it for ways that I can defend later, but it does give you the answer that some systems, so this is an example of a globular cluster, which is about 10 to the 5 stars. This system doesn't count as being thermodynamic. It has certain statistical mechanical features, but it doesn't count as being thermodynamic because there aren't any equilibrium states. So it's kind of, I think, in some ways, a tough bar to pass this criterion of what it takes for something to behave the right way. So I'm going to scoot through these details very, very quickly. The answer to the question is yes, and I can go through some of the technical details later if you want to hear more about it. But roughly, we can think about black holes as having equilibrium states. This involves something called the membrane paradigm, where you imagine cloaking the event horizon in a membrane where you assign all the properties to this membrane. And when you do that, you find you can assign certain thermodynamic properties that are unchanging in time, so they look like equilibrium states. And we can think of them as being stable in the right way. And we can also think of there being these particular type of processes, which I'm actually just not going to talk about at all. But we're going to come to the conclusion, which is they do behave in the right way. Okay, so black holes behave in the right way to have thermodynamics be applied to them. But you might think, well, how is that going to help us with this original question of whether there was just an analogy or an identity? And here, I think functionalism is really unhelpful because it kind of blunts the difference between analogy and identity. So X is analogous to Y if X behaves like Y. Pendulums behave like circuits in certain ways. And functionalism says X is Y if it behaves like Y. So showing that black holes behave like thermodynamic objects doesn't tell us the difference between saying black hole entropy is analogous to thermodynamic entropy, and black hole entropy is thermodynamic entropy. So the kind of door is still open to the claim that this is an analogy just like simple harmonic motion. You know, you've shown that there's certain features in common between pendulums and circuits. There's the kind of overarching features here. Maybe you've got to say there's a second derivative on the left-hand side related to the right-hand side. Here, you said there's something in common, which is equilibrium states and quasi-static processes, and you've shown they apply to both, but that doesn't necessarily mean that it's anything more than an analogy. So the claim is, great, you've shown that black holes behave like ordinary thermodynamic objects, but pendulums behave like circuits, so you've not really solved the problem. So whilst I think functionalism doesn't help us with this question, we know that there's a clear difference, right? So in the simple harmonic motion case, we had the kind of x was the spatial displacement of the pendulum, and that was behaving like charge, but we don't say that spatial displacement is charge. That seems like a bonkers thing to say. Likewise, we don't say for other terms that are related in the right way, capacitance is spring constant, right? That just seems like a weird thing to say. What we want to say is capacitance is to spring constant, like spatial displacement is to charge. I've got that the wrong way around, but you know what I mean. It's just one is to another thing as the other is, rather than this thing is this thing. And the reason why we don't say this, I think, is because we're clearly applying it to different types of target systems, right? So in the case of the functional realization, and I think I've got a picture coming up. Yeah. In this case, right, in the thermodynamic case and statistical mechanical case, these are two descriptions of the very same system. Whereas in the case of can I get the picture back? In this case here, right, we've got two distinct target systems. Right. So that's why in the analogy case, we don't make these identity claims that perhaps are made in the cases where you have the same target system. So what does it mean for the description to apply to a distinct target system? Well, one way of thinking of them as being distinct is to say that they're not interacting. So the way then to show that we don't have distinct target systems in the black hole thermodynamics case is to show that we can have a black hole interact with an ordinary thermodynamic system, like a gas of photons, for instance, and together behave in a suitably thermodynamic way. And I think this has been shown. So Karina Prunkel and Chris Timpson had this nice paper where they show how a black hole can be in equilibrium with a photon gas, which you might think is kind of surprising, right? Black holes like gobble things up. So getting it in equilibrium with another system is a slightly delicate matter, but it can be done. It involves having the box be like the right size. But you can show that you can have a black hole in equilibrium with a photon gas, and it can undergo a reverse Carnot cycle. And a Carnot cycle, I haven't explained what that is, but for those that are familiar with it, it's kind of the typical thing of thermodynamics, right? So kind of it's about how you kind of isothermally expand and compress a gas in order to get work out and drive your steam engine. And it's what you use to define thermodynamic entropy in the first place. It's kind of like this key part of thermodynamics. So the fact that you can show how a black hole and a gas can interact in this way, I think shows that there are, it's clearly behaving in a thermodynamic way. And yeah, there's various nuances that's not particularly easy. Lots of hard work is required in order to show that you can do this. And another way to see that the things can be, that the two systems can be in contact is you can put a black hole in contact with another system via Hawking radiation. So the idea is that the radiation coming from Hawking radiation is in equilibrium with the photon gas, for instance. So I think this shows that we can have black holes and ordinary thermodynamic systems behaving in a thermodynamic way together, but interacting. It's not like the two separate systems like the pendulum and the circuit. Okay, so they can interact in the right way, but I think there's even stronger reason to think that they're thermodynamic, which is the joint system, so the black hole and photon gas, for instance, is governed by a law called the generalized second law. And what this law tells you is that entropy is fungible in a certain sense. So if you have a decrease in black hole entropy, that can be kind of compensated for by an increase in the exterior of the black hole. So if you imagine you've got your black hole and it's surrounded by a gas, the black hole gobbles up some of the gas, that increases its mass. So the event horizon, the area of the event horizon increases. So that means that the black hole entropy is increased, even though the entropy of the matter outside the black hole is decreased. So the generalized second law says that together these two quantities can't decrease over time. So there's kind of, you can think of it as a generalized entropy, black hole entropy plus normal entropy. Together that quantity can't decrease, even if individually each of them can. And so this means that, so one way of thinking it is I throw a cup of coffee into a black hole, that decreases the ordinary entropy of the rest of the universe, but it's increased the entropy of the black hole. And likewise, when the black hole evaporates by kind of smoldering away with Hawking radiation, it's shrinking. So its black hole entropy is decreasing, the area is getting smaller, but the entropy of the rest of the universe is increased. So together, the entropy doesn't decrease. And this is completely unlike the simple harmonic motion case, right? That's not at all like the case of pendulum and the circuit. Well, we don't think of them as exchanging quantities in any way. So the generalized second law, I think, really kind of is the final nail in the coffin for thinking that this is just an analogy between these theories. Okay, so now for the bit that I would like some help on. So I think we can safely say that black holes are thermal objects, but how should we understand the claim that black hole entropy is thermodynamic entropy? And this is not particular to black holes, right? I think this is like a really vivid arena for the question, but it comes up in loads of other places. So people often, a kind of pet peeve of mine is when people say that mean kinetic energy is identical to temperature. It's not. It's only for an ideal gas. For loads of other systems, you can talk about temperature of other systems like magnets. They don't have mean kinetic energy. So it's only for an ideal gas that mean kinetic energy is temperature. But nonetheless, we still say that this thing is this other thing. Likewise, we could say that Gibbs entropy is thermodynamic entropy. What is it that we're saying when we do that? So I think the kind of completely hopeless option to kind of put that to bed is that they're not conceptually the same, right? So this is exactly what the kind of Sklar worry at the start was about statistical and non-statistical quantities when we say the temperature is mean kinetic energy. They're not conceptually identical. Likewise, the Gibbs entropy is talking about probabilities, not talking about heat flow at certain temperatures. And likewise, the black hole entropy depends on gravitational constants, Planck's constant, and the area of the event horizon. Right? That's very different from like heat flow in contact with a bath at certain temperatures, which is what's going on for the thermodynamic entropy, which I haven't given you a definition of, but you can take my word. The other place where identity comes up in the philosophy of physics a lot is with respect to quantum particles, where it looks like the two particles share all the same properties. And so it looks like by Leibniz's principle of the identity of indiscernibles, that they look so similar, it's hard to see how we're going to say that they're not identical to each other. There's a big debate in the philosophy of physics about this. Here, we've got quite a different situation, right? There, the problem was things look too similar to not be identical. Here, the problem is they're not similar enough to count as being identical. So I don't think that helps us, though, just to flag that that's a related debate. So I think the thing we should say instead is that when we say X is Y, we're not using the is of identity, but the is of predication or instantiation. So the difference between saying the morning star is the evening star, that's the is of identity, versus Socrates is mortal. So on this view, that means that what we're going to do is we're going to say the black hole entropy has the property of being thermodynamic, or it instantiates the black hole entropy. Sorry, the thermodynamic entropy. The black hole entropy instantiates the black hole entropy. So to anticipate the objections that might come to this, and I've just realized that I haven't got the bullet points to appear all at once, so you're going to just get hit over the head by a whole load of text now, brace yourself, is that people might think that maybe we could still have the is of identity rather than instantiation. So you might want, I can imagine somebody saying to me, look, Clark Kent and Superman are conceptually very different, but nonetheless are extensionally equivalent. And I think that fits with how people used to think about intertheory relations. You know, we thought there was this thing, thermodynamic entropy, but it really turned out to be the statistical mechanical entropy. So we had this macro quantity, it really turned out to be this micro quantity. This is a bad way of thinking about it for intertheory relations. But independently, it's very rare that the two quantities are actually going to be extensionally equivalent. So to give you what I think is a really vivid example, if you're already familiar with some of these examples, is the Shannon entropy, right? That's defined in all these different cases. This is the entropy associated, the information theory entropy. So you can have the Shannon entropy of a bit string telling you about how much information is contained, how much you learn by receiving that bit string. And that is a very, very different thing from the statistical mechanical entropy. In certain cases, they coincide when you have the right type of probability distribution. But the Shannon entropy is defined in loads of places where we think you're not going to talk about the statistical mechanics or the thermodynamics of computer messaging, for instance. Maybe there's some caveats there. But another example would be temperature and mean kinetic energy. So loads of things have temperature, not just ideal gases. So those two terms are not essentially equivalent. And likewise, in the case of thermodynamics, it's defined outside the realm of black holes. And so the thermodynamic entropy is not extensionally equivalent to the black hole entropy. I think it's particularly clear for the generalized second law, right? It just makes a complete nonsense of the law if you think that they're referring to the same thing. So you're saying the generalized second law says one quantity goes down, that's going to be compensated by an increase in the other quantity. But if it's referring to the same thing, you can't have the same thing both increasing and decreasing. So I think this is kind of an unhelpful way of thinking about it. And I think it leads to this confusion, which is, you know, the obvious reply to that example about one thing going down, one thing going up, is that one is the entropy associated to certain degrees of freedom or certain parts of your system, and the other is the entropy associated to another part of your system. So you've got to kind of keep those two things separate. So this is so I think I don't think we want to think of it as the is of identity. Instead, I think we should think of it as the is of instantiation. And then there's going to be this optional extra where you can think about it as functional realization. So in the case where you've specified a particular context, the degrees of freedom in a particular system. So if I'm talking about a gas, I've specified, okay, I've got this box of gas, it's at equilibrium, and I'm only interested in this kind of thermally isolated case. Then I can say that I'm missing some subscripts very unhelpfully. So then I can say that the thermodynamic entropy and the Gibbs entropy pick out the same quantity, like in this case here, right? Here we've got the kind of thermodynamic description, the stat-mech description. In the case where I've specified all of the details, then they kind of pick out the same thing in the world. So that's kind of my nod to the objection on the previous slide, right? There's a sense in which that objection has something right about it. That's how I think you should overcome it. So we've got this kind of token identity in those particular cases. But most of our laws and stuff are all defined at the type level. We're interested in thermodynamic entropy, not just in particular cases, but in general. And in particular, even though this is kind of a nod to the previous objection, this is not going to be the kind of full-blooded identity in the following sense, which is, so one way of talking about lots of things I've mentioned is to say that temperature is realized by different quantities in different systems, or that entropy can be realized by different quantities in different systems. So it's multiply realized. But just because I say that the Shannon entropy is the Gibbs entropy in certain cases, and the Gibbs entropy is the Shannon entropy, is the Gibbs entropy in other cases, we don't then get to say that one thing is then is the other thing, right? So, or to give you another example, temperature is mean kinetic energy in one system, temperature is something else in another system. We don't then say that those two things are the same thing, right? So I'm trying to think of a good example off the top of my head. Right, so if temperature is realized by surface gravity in a black hole, we don't then say that mean kinetic energy is surface gravity, right? There's no transitivity. So instead, I think it fits with this package where we say that this is, when we say X is Y, it's this is of instantiation. And that fits nicely with this idea of it being a kind of functional realization. And so when we say the black hole entropy has a thermodynamic nature, what does it mean for it to have a thermodynamic nature? It seems like at that point, there's various different options you might want to go with. The way that I would favor is to say it's playing the right role, but there's room to have like a different view about what it is for something to have a thermodynamic nature. I just think that that's in fact how we go about evaluating it in physics. So the question I guess I have for you is, how substantive an assumption do you think this is? For me, it seems like this is a very natural understanding of how people talk about these things. To the extent that functionalism is this reigning presumption of science. But perhaps there is something more controversial going on. So maybe you can tell me why it's too controversial. We don't have too much time, so we could talk about the status of the generalized second law later. The interesting question is, we said there's this quantity that can't decrease. This generalized entropy, which is the sum of the black hole and the normal entropy. The generalized second law said together those can't decrease. If one goes down, it's compensated for by the other. To what extent is that just the ordinary second law applied to that joint system, or is it a distinct law? I think that depends on how you want to individuate different laws. Okay, I will be quiet soon. So the key question is, what does it mean to say that the black hole entropy is identical to the thermodynamic entropy? I said that functionalism gives us a way to understand these X is Y claims that come up in physics in a way that allows for certain differences, which I think that fits nicely with this is of predication or instantiation. But functionalism is kind of not very helpful for those wanting to rebut the claims of mere analogy. Functionalism on its own can't do that, remember, because analogies require the same behavior. Functionalism says X is Y if the same behavior, so it can't tell the difference between analogies and something stronger. So in order to get rid of the claim that it's just an analogy, we need to show that ordinary systems or ordinary thermodynamic systems and black hole systems interact in the right way. And Hawking radiation was really important here. So I think I kind of slightly downplayed it in this version of the presentation. But Hawking radiation, to fit into Baptiste's talk, Hawking radiation comes from the semi-classical gravity. So it comes from like a rung down in the kind of fundamentality of theories than general relativity. And it's really the kind of crucial thing, I think, for kind of cementing this idea that black holes are really thermodynamic systems and how they're going to interact with other systems. So whilst we've been talking about this kind of like macro theory and how it relates to these other theories, like lots of the power is coming from this semi-classical gravity. So yeah, black hole, Hawking radiation is really important for this. And that's kind of unsurprising, right? That the whole original story goes, look, there's a kind of similarity. Oh my God, Hawking radiation. No, it's that they're identical, right? So this is kind of unsurprising. Okay, I think that's everything. Thank you very much.